all. Thank you all for coming out to the DataViz meetup. Just a couple quick announcements we have. I think Bill wanted to give an announcement real quick about his meetup.
Hey everybody, so I'm Bill Schwanitz. I'm one of the organizers for the Smart Columbus Open Data Enthusiast meetup. It's the meetup that founded after the hackathon from the Smart Columbus stuff. We're looking for people of all varieties, including data visualization. It is a working style meetup, so if you're interested, I don't care what your skill level is. The idea is it's part of the community, so people, experts, great, come and help. People that aren't quite as expert, come and learn. So that's all. Ping me after if you have any questions.
When do you meet?
The next meetup is, I believe, October 2nd out at OCLC. We roam around a little bit in the downtown area. I can go into more details, but the next one's OCLC. And then December is either going to be a meetup or, at least for the other meetup that I run, which is the DevOps Columbus meetup, we've tended to treat December as a skip month because of the community and holidays and everything. We do the meetup of meetups community fest, our holiday party thing. So there might be a December, might be January.
Cool. Thanks for that.
I'm Mike Burton. I'm the director of the data science program, new data science program at Ohio University. I teach down there, but I live up here. We're launching a data analysis graduate certificate in January. It's mainly, it's more stats oriented than visualization oriented, but it's Python, R, and similar tools. Commitment to open source, and the target audience is people who don't necessarily have a stats math background, but to give them a foothold to launch themselves into more serious data science down the road. And of course, I have business cards.
Great. Anybody else have any DataViz related things they'd like to announce?
It's 3 semesters.
All right, so I see a lot of returning faces here, but for anybody who's new, my name is Eric, and my co-organizer over here, Eric, and Anaya is somewhere back. He's back there in the corner. So if you have any questions or want to speak in the future, you can come to one of us after the meetup. I hope everybody had a chance to grab some food. One quick announcement for anyone that's interested in art. There's actually an exhibit going on at the Columbus Art Museum right now. It's called Measures of Humanity. Had a chance to go last week with Eric and Josh, and it was really cool. It's free on Sundays if you ever want to go. Just a recommendation real quick. So I'll go ahead and introduce our speaker. This month our speaker is Sankir. He is a data scientist who graduated from the University of Nevada, Reno. He has a master's in data science, and he taught for 2 years statistics, Python, and linear algebra. And tonight his topic for his speech is focusing on data visualization using Python. So without any further ado, thank you.
Thanks, Eric. So yeah, my name is Sankir, and well, I have a master's degree in computer science. So I'm pretty sure that you said data science, but yeah.
Oh, sorry.
So that was the one thing I wanted to clarify. So before starting, I would like to know my audience. How many of you have worked with Python for more than 6 months? Wow, that's nice. So rest of them, have you started with Python, or are you completely new with Python? No. Okay. So the reason why I asked is to limit my usage of technical terms. So before I start, I would like to go over the basics. So this is a Jupyter notebook. So before I start, Anaconda is a Python distribution that is used to develop machine learning and data science related applications. Jupyter notebooks provide an interactive Python environment where you can type the code and see the results immediately. Additionally, you can add text as well as images to it. These were earlier known as IPython notebooks. Data frames. Data frames are Python's data structure to hold tabular data. These are considered the bread and butter of data science. So I find it easier to explain the concept of data frame with the help of an Excel sheet. A cell in Excel is considered a field, whereas a row is considered as an observation, while a column is called a feature. I've imported the packages pandas here, and I've read the file Hogwarts, which is stored in hogwarts.csv. So this is how the data looks like. It has 4 rows and 5 columns. Please note that the indexing starts from 0 in Python. That's the reason you see 0, 1, 2, and 3. To access a particular column, you pass the name of the column enclosed in quotations to the data frame. I am interested in the column house here. So I pass the variable house, I pass the column name house to the data frame, which is enclosed in single quotations. And this gives me the columns, the values of the column. Linear regression. Let's consider you have a data which has x and y variables. Linear regression helps build a model that predicts the future values of x. Assume that I have a data set regression reg.csv, and these are the values x and y. When x is 1, y is 3. When x is 3, y is 5, and so on. Eyeballing the data, I can say that y equals x plus 2. Now if you go back to the linear algebra from your high school, this is in the form of y equals ax plus b, where a is the slope and b is the intercept. We use Python's NumPy's length-based method, which gives us these regression coefficients, which are slope and intercept, in this case a and b. The need for data visualization. So I'll go ahead and import the necessary modules. The first 2 modules, NumPy and pandas, are used to perform statistical calculations as well as clean the data. The next 2 are Matplotlib and Seaborn, which I'll be using for data visualization. The need for data visualization can be better explained using Anscombe data. The data is stored in anscombe.csv. Using pandas read CSV method, I read the file, and this is how my data looks like. I have 11 columns and 8 rows. No, 11 rows and 8 columns. The columns are x1 through x4 and y1 through y4. As you can see, the values are quite different. Let's go ahead and to perform the summary statistics and linear regression efficiently, I divided this data into 4 individual data sets. Data 1, data 2, data 3, and data 4. I'll go ahead and compute the means of x and y variables. Now when I look at this, the means of x and y variables are pretty similar. Let's compute the standard deviation. They are the same as well. I'll go ahead and use polyfit method to get the regression coefficients. And yes, they are almost the same again. So basically, just by looking at this data, I can conclude that they are the same, right? Based on the summary statistics. But we have looked at the data earlier. The values are not similar. So eyeballing data, looking at the summary statistics, and drawing conclusions from it is not a good idea at all. Let's go ahead and visualize the linear regression. So for the values of x, I use 3 and 15. And I plot the regression line. You see, the line is it does a pretty good job, as is in the case, it is decently aligned with the data points, right? The data points are not really far. This is for data set 1. Now let's look at data set 2. Again, the data, it is closely aligned with the data points. However, when you just look at the data points, they form some sort of curvature here. You see, linear regression might not be the best option here. Data set 3. So this does a pretty good job as well, but you see the outlier here, we are missing it. And for data set 4, we have the same regression line. However, a line which is parallel to y-axis and has an intercept 8 might be a better model, right? That way it'll be passing through all the data points. However, again I'll be missing the an outlier here. So for this, for the data sets 3 and 4, I need more data. You see how my inferences have changed once I visualized? So that's the power of data visualization. So this is how they look like. So you can clearly see the difference. Even though the data points are different, the linear regression line is the same. Look before you leap. It's always a good idea to explore your data before jumping into conclusions. So how do you do it? Using statistical analysis. You have descriptive statistics, you have inferential statistics. The goal of EDA is to explain and explore. Explore your data and explain your findings or communicate your inferences. If you haven't used statistics for a while, you can refer to this chart I've created. So you can see EDA is here. We have now graphical EDA both for univariate and multivariate variables. So we'll be focusing only on the graphical EDA here and here. Data visualization using Matplotlib. Matplotlib is a plotting library which gives you a highly customizable way of plotting the graphs, and also gives a great control on each element of the plot. I'll go ahead and import the modules again, the 4 modules. By specifying percentile matplotlib inline, we don't have, so this makes sure that we are plotting the graphs within the notebook. However, it also eliminates the need of writing plot.show method, which you have to do if you are using a different editor. Matplotlib supports 2 styles of creating plots. One is functional approach, and the next one is object-oriented approach. Let's go ahead and look at the functional approach. So I create 2 arrays, x and y. X takes the values -4 to +4, y takes the values -2 to +6. Plotting a graph using Matplotlib is as simple as calling the plot method and passing x and y to it. So this piece of code here, this generates the plot. And do not forget to label your axes. You can do that by xLabel method. I can also assign the title name. I can also pass the title name to the title method. So x value is in the x-axis, squared value is in the y-axis. Okay. So I assigned the wrong label here. So it was supposed to be y, and then even the title. I should format it. Sorry about that. Multiplots. You can also plot multiple plots in a single figure. You can do that by using subplots method. It takes the arguments, number of rows, number of columns, and index. And this is how the syntax looks like. Plot.subplot method takes n rows, which stands for number of rows, and n columns, number of columns followed by index. So here I have created 2 plots. So as you see, it specifies that I need 1 row and 2 columns, and the first one takes the argument 1. This tells Python to plot this graph in the first row and first column. You see R here, this plots in red, whereas G plots in green. And you have a bunch of more arguments that you can pass. We'll be going over it in a while. Object-oriented method. So what we do in object-oriented method is we instantiate a figure object and pass the attributes and methods to it. This is useful when you're using multiple plots. By using figure method, plt.figure method, this creates an empty figure. A new figure, you can think of it as an empty canvas. And you can also pass fixed size, which actually specifies the size of the figure. You can add axes using add axis method. And this is again straightforward. So you can pass the variables, arrays x and y, and specify the color of interest. Always label your axes. In this case, object-oriented, which is an object-oriented method, I'm using setXLabel as opposed to xLabel, which was in the functional approach. You can add legend by using legend method, which takes an argument log. Log takes the values, numeric values, 0, 1, 2, all the way to 9. 0 specifies that, so 0, what 0 tells Python is to pick the best location based on the graph. So here are a bunch of arguments that it takes, and this is what they mean. So 1 is for upper right, 2 is for upper left, and so on. Did you notice anything different in this graph? Anybody?
You've got the data points on the same this.
Yes, that's, but just at the plot, not the,
No,
anybody?
The axes aren't labeled?
Yes, I did not label my axis there. Please label your axis. Multiplot. So you can think of a multiplot as plot inside a plot. That's like the inception stuff. What you can do is, so this is the first plot. This is straightforward, and this is how the second plot looks like. It's a parabola. Now I can plot both of them in single figure. Notice that I have created two axes here, axis 1 and axis 2. And then I plot x and y, just like as I've done in the previous example. And now you see, here it is. You have to play around with the positioning here by adder. You have to play around with these, the inset axis and the main axis, to finally figure out what's the appropriate position. Always limit the number of subplots to 3. Again, this is like a Christopher Nolan movie. You might get it wrong the first time you watch it, so it will take a while to play with the axis. Formatting the plots. So you can format the plots by adjusting the figure size as well as DPI, which stands for dots per inch. Fixed size accepts width and height, whereas DPI accepts dots per inch, the number of pixels. So here are the arguments. You can specify the figure size by also to the subplots method here. Coming to export figures, you can Matplotlib supports all major file formats. It supports PNG, JPG, PDF, and so on. You can use savefig method and pass the name of the file to it. Colors and styling. Most of the colors, the values for the arguments take the first name, except for black, which takes K. And also styles. A hyphen draws a solid line, whereas double hyphen draws a dashed line, and so on. So here are the arguments. What's the coolest thing about it is you can pass a combination of this. So B hyphen hyphen means a blue dashed line. So here you go. This is what it looks like. So B hyphen draws a solid line, whereas G double hyphen draws a dashed line. Coloring can also be done using hexadecimal code, because if someone is using a particular shade of it, you might not get the name of it correct every time, but actually you can use the hexadecimal code. Matplotlib supports that. And yes, Matplotlib is smart enough to understand if you are actually specifying the hexadecimal code or just the argument R or B. Logarithmic scale. This comes under scaling of your data sets. this is very useful when you're trying to build a model, a predictive model. The reason why we use logarithm scale is, I'm currently working on a project which has a bank, which is on a bank marketing data set. One of the column or one of the feature is salary. So it ranges anywhere from 40,000 to 250,000. And another column is gross domestic product. Now this is usually in 1 or 2 digits, right? So the scale is quite different. So for those reasons, now if you want to plot it, it might be completely different. So for that, for things like that, you might have to use logarithm scale. So this is the code snippet that draws the logarithm scale. So this is the normal scale, which is quite, it's not so good. And then logarithm scale, and you can actually specify the powers of, in powers of 10. Ticks and tick labels. Assume that I have a similar data, and now I'm trying to find the x square and y square of it. If I want to label on a particular point on x-axis or y-axis, then I can use x ticks. So here, I would like to mention the label for 1, 4, 7, 9, and 10. And on the y-axis, 0, 200, 400, 600, and 800. I can do that using x ticks. You specify the number, and x tick labels takes the numeric categorical values or string values. So this is what the graph looks like. If I do not use the x ticks, so this is how it looks like. It basically plotted everything all the way from 0 through 10. So that's the difference. Data visualization using Seaborn. Seaborn is Python's data visualization library that plots really attractive statistical graphs. Your data is usually made up of numeric and categorical types. So for numeric data, it's very important to understand the distribution that it has. To do that, Seaborn supports majorly three different types of plots: pair plot, disk plot, and joint plot. So I import Seaborn as SNS, and then I import the tips data, which is provided by Seaborn again. Looking at the data, I have 7 columns, and 3 of them are numerical: total bill, tip, as well as the size. So I can use disk plot method to understand the distribution. However, when you use disk plot and pass the column of interest, it also uses KDE here. You see the curve here? You can get rid of that by specifying KDE is equal to false. Here you go. And also you can play around with bins to find the optimal bin size. Usually the optimal number of bin size is square root of the number of observations. A joint plot is so using a joint plot, you can plot 2 different numeric columns. As you see, it plots the histogram, which is the distribution, as well as a scatter plot. By default, Seaborn uses a scatter plot. You can actually specify your own kind of plot. If you want to use regression plot, residual plot, or hexagonal bins, you have all the options to do that. So to do that, you pass kind is equal to hex in this case. So these are the hexagonal bins. So it's pretty simple. You pass in the value of x, which is the total bill, and the y label, y-axis should be tip, and specify the data frame to the argument data. this is the linear regression line, and you see this band here, this faded band. This is the 95% confidence interval. Now, when you use joint plot, it automatically gives you the Pearson correlation here. You see here Pearson R, 0.68, and value of P is very low. Assume that you want to plot more than 2 numeric variables. You can use a pair plot in that case. If you just pass the data frame, Seaborn will automatically take all the numeric columns and plot them in one single plot. So here, since I have 3, which are total bill, tip, and size, so it gave me 9 different plots. As you see along the diagonal, we have histograms. However, if you would like to filter the data or compare the data with a categorical variable, by all means you can do that by specifying hue. So here the categorical variable that I am using is sex. Hue is equal to sex, classifies the data, and here is the legend that you can take a look at.
So for each value of the sex column, you would get a different color.
Yes, pretty much. So if you have multiple classes, you'll get multiple. If you have 4 classes, you get 4 different colors. Categorical plots. If you have categorical data and you would like to plot only a single column, then you can do by count plot. It basically just returns the counts. This is very important. I mean, in real world data sets, usually the classes are imbalanced. I mean, you have category of one which are highly, the number of observations of one class are really high, and the observations of another class are really low. One example would be the number of fraudsters in a bank data set. So you do not have many fraudsters. It can be anywhere between 1 to 2%, right? That's still a huge difference, 98 to 2. Bar plot is similar to count plot. However, you pass a numeric column to it. Here, I would like to know the mean of it. So I pass the total bill as Y and sex as X, which is a categorical column, right? So the estimator by default is mean. However, if you would like to use, so this is the mean. This says that the mean for male class is slightly above 20, whereas for female is close to 20, but less than 20. However, since this is the mean and you would like to find the standard deviation of it, you can do that by specifying np.std. np is the alias for numpy. Std is standard deviation.
What's the flag thing? What's that one?
This one?
The black, I'm assuming that's the flag size. What is that? What does that show?
This is
The
the standard
whiskers.
deviation of it.
I think he means the whiskers.
Yeah, the black vertical line in the middle of male and female.
Okay, so I'll be going over it
Okay,
in a box and whiskers plot. You'll have much more
Sorry.
clear idea. That's fine. So here I've passed standard deviation to it. Notice here the value of male is slightly above 20. That's the mean. And for standard deviation, it's now less than 10. Box plot. They show the spread of categorical data among different classes. Here, the categorical data I've used is day. I have 4 different classes here: Thursday, Friday, Saturday, and Sunday. Now, you can see that over the weekends, the values are a bit higher compared to Thursday and Friday. Oh, just give me a quick minute, just 1 minute. An email was supposed to be here. do not have the image. So I'll share this notebook, just make the necessary corrections and share the correct version. And I'll also update in the comments what is missing. So hue variables, you can also use it in box plot here. Notice earlier we had only 4 columns, 4 plots. Now we have 8, one for each smoker here. Smoker here is my categorical variable that I've used as hue. Strip plot. A strip plot is a good complement to a box plot. However, this is really good when you have smaller to medium data sets. The reason why I say small to medium data sets, because you know that the values below 30 are higher. You have more values below 30 than the ones above it. But you are not sure how apparent they are, how many values are below 30. To do that, you can specify jitter is equal to true. Now you see, instead of one line, they are actually scattered. Right? However, the dots are still overlapping. Right? To do that, you can use a swamp plot here. This does not overlap any data points, and it kind of gives you a sense of distribution, what each class follows. You can see the data is very widely spread for Thursday, Saturday, and Sunday, because the points are really scattered. A violin plot also gives you the distribution of a categorical data. However, it uses a kernel density function rather than just the data points. Remember, we had data points here. They were not actually colored. They were not actually solid. However, it uses KDE here, kernel density estimation, rather than just the data points. So you see that here, where the peak is a bit more bulging, that is where your most data is. You can also pass hue to it to filter the data based on a particular column. However, this kind of is not visually appealing, right? So what you could actually do is, by specifying split is equal to true, it plots both the classes in one violin plot. You see the difference here? So that's the difference. Now, why do I use Python to visualize? 2 reasons. Coding. People have been managing other people to get things done. This has been going on for thousands of centuries and thousands of years. Centuries, thousands of years. Well, in 20th century, most of the jobs have been already automated, right? But, okay, think of it this way. On an average, around 3.5 billion searches are being made. Machines are doing that stuff for us. Humans are not doing that. Imagine how much time it would take for a human to do that, to do one Google search. So again, the machines are doing that stuff. So what I'm trying to tell is, it's no longer talking to humans that get things done. It's talking to machines. And how do you do that? Coding. Another thing, are we control of our decisions? Well, not really. Here's an example. You see this graph here? Is it visible? This one? Yeah. You see this graph here? This was an organ donation program. On the right, you see the countries which have really extremely high values for enrollment. And on the left, you have extremely lower values. Experts say that the organ donation thing, or opting for organ donation, can be a matter of culture, or probably sometimes even religion. Now, when you just look at the data sets, just look at the columns closely, you see that likewise countries, or similar cultured countries, have indeed different behavior. We have UK, which has 17, and France, which has 100. You have Denmark here, which is 4, and culturally similar country is Sweden, which has 86. Then a further research was made, and then it turned, okay, and before that, before I talk about research, let's talk about Netherlands here. So Netherlands has the highest value of the smaller group, 28. Turns out, it got that higher number after the government has been sending emails begging everyone to get into the program. So think of it this way. Begging gets you to 28. But countries on the right did something better, right? They did much more smarter thing than begging. What did they do? It turns out this thing here. It turns out that the form at DMV played a crucial role. So Form A says that check the box if you want to participate in the organ donation program. So people did not check it, so they did not participate in the program. Form B says check the box if you do not want to participate in the program, which the users didn't check again. Well, they did not participate in the program, but they joined the program, right? That's what it means. So it was not about religion or culture. It was about the form. Similarly, it's not just about data. It's also about visual evidence. Thank you. And do you have any questions?
You might go back to the box and whiskers plot to clarify what that was.
So it's basically the percentiles, the 50, 75 and outliers that it gives. Is this the one or the one?
Two back, I believe. Yeah, that one.
So this can act, I can actually explain better in this, with this. So this is called IQR, Interquartile Range. Are you familiar with it?
I'm not a stats geek. No.
Okay.
I was
So-
just curious. It threw me for a loop. I've never seen it that way before.
Okay. So what it says is anything beyond this whisker is an outlier.
Okay.
Okay. So we have a bunch of outliers here, and you see the line in the middle.
Yeah.
That's 50th percentile, which is nothing but the median.
Got it.
Okay.
So and then the upper and lower horizontals, those are your mid and average. Is that what that's showing? What is there significance to for Thursday the horizontal line on the bottom and on the top? What does that show? Is that the bounds of?
Yes, pretty much. So the data is distributed from this and this, but that doesn't mean the whole data is distributed within this. There are a few more here, but we can
Those
treat
are
them as
outliers.
outliers.
Okay.
And also, any outlier is not necessary, and it's just an erroneous data point. That doesn't mean you have to delete it or get rid of it. For example, there is a US elections data between Obama and his counterpart. So there are few outliers. Well, there is no proof that an electoral fraud has happened. So they are just values of extreme things.
Okay.
They are not really outliers. If some sort of fraud has been recorded, then you can treat them as an outlier and just get rid of it.
Got it. Thanks.
Yep. And any more questions? Yes, please.
Can you talk about the graph just before this, the two box plots? So you use standard deviation of
Here?
total bills, yeah.
Mm-hmm.
So how did you apply the standard deviation function? What does that mean to this distribution of total bills?
So,
Or
no, it's not just a distribution, it's just the plot. So here you see estimator is equal to np.std. So if you go back further, I've imported numpy as np, right? So np is the alias, and it has a function .std, which stands for standard deviation. So by default, if you do not specify any estimator, it uses mean here. It uses mean here. However, if I use estimator is equal to np.std instead of using